Hello guys, what's up? I'm Mohammad Fad, back with the second episode of our machine learning course. Guys, let's get straight into the point. Today's video is about the gradient descent algorithm. Guys, in the previous episode, I explained you what is the cost function and I explained you a little bit about the hypothesis function in linear regression. So we talked about a little bit about linear regression, and then we talked about what the cost function is and the importance of it in machine learning and neural networks. So today, at first, I'm gonna recap what we've learned in the previous episode, and then I'm gonna explain to you what the gradient descent algorithm is. Now, gradient descent algorithm is used in all over in mathematics, in, I don't know, maybe statistics. I'm not really sure about that part, but it's really useful in machine learning and in neural networks, deep learning, all of this stuff. So without further ado, let's dive right into it. Alright guys, so here is the recap from the previous episode. So let's take a look at how linear regression works. This is a graph which represents the problem that we have. The x-axis is the input features that we have. As I told you in the previous episode, the inputs are called features as well. Now I'm just showing a problem which has only one input, but in most of the programming problems, machine learning problems that we have multiple inputs. So we have the input here, and I'm gonna show the input by x, and we have the output for that. We say for the specific input x, we will have this specific output y, and we have a bunch of these values all around our model. And these are basically called training examples, and they come in the training set. So as I said, the objective in linear regression is to find the mathematical function that fits the data really well. That way we can have an estimate for the values that we don't have the answer for them yet. So as you can see, the input, this point in the axis, we don't have any answer for it yet because it doesn't exist, right? What we try to do is to find the mathematical function, a linear function that fits this data really well, and then we can use that function to have an estimate of the output for that specific input. Then we talked about what the cost function is, and the cost function is basically a measure of how accurate we are with this mathematical function that we found for this data set. And by the way, this mathematical function is called the hypothesis. This hypothesis function will look like this. We will have y equal to, and this y that I'm saying here is our estimate for the input x, right? Because this whole mathematical function is just an estimate for the inputs that we don't have the answers for it. So the hypothesis function looks like this. We have y equal to theta x plus theta times x, and so on. So as you can see, this function that I've drawn here has two input features. We only have one in this example, so I'm gonna miss the other one. We later learned that this x over here is not counted as an input and is equal to 1, because most of the mathematical functions, the linear ones, they all look like this. We have y equal to some value theta times x plus some other value theta 2, let's say, right? This is how the linear function looks like in mathematics. So we try to show this term over here by theta 0 and x 0. So when I draw this for you, it means we are showing this. So this is how the hypothesis function looks like. And what we try to do is to find a really good estimate for this theta value. So we have a nice mathematical function for the data set that fits the data really well. And the cost function is the measure of how accurate we are with this. Now, the really good thing about the cost function is the graph it makes against the theta value. So if I want to show the graph to you, it will look like this. Before I show you how the graph looks like, let me tell you what the equation for the cost function is. Alright, so here's how the formula for the cost function looks like. And the way that we find our accuracy is by using our hypothesis function that we've just developed on the set, on the data that we already have, to see how far away we are from the actual answer that we were supposed to get. So if we use the hypothesis for this value over here, and we get an answer with a value of this much, then we know that we are this much far away from the answer that we were supposed to get. And this cost function basically tells that to us. And this term over here means we do this for every single data that we already have. And by doing so, we get an estimate of how accurate this mathematical function or our hypothesis is. Then we use what we're gonna be learning today. We use gradient descent to change these parameters of our hypothesis to get the better mathematical function. So let's say we start by a function that looks like this. Then we use the cost function and we find that we are this much and this much and so on. We are this much far away from the answer that we were supposed to get. Then we use gradient descent. I'll let you know how we do it, but we use that to get something closer to the actual one that we should get. So we get something like this. As you can see, it's a little bit closer to the actual answer that we are supposed to get. Then we keep doing this until we get this really good mathematical function that fits all the data. Not all of it, but most of it really well. Now, as I said, the thing that makes the cost function so special is the graph that it makes. Let me draw that for you here. So we have the cost function value, g of theta, and we have the parameter theta. It can be 0, 1, or anything. This parameter that we have here is referring to the parameter we have for the hypothesis, for this function, for this mathematical function that we are trying to make that fits the data really well. And we probably have a sweet spot with our parameter theta that makes this really nice hypothesis which fits most of the data really well. So the function that it creates, the mathematical function, is a quadratic function that looks like this. So what this is telling to us is that we have a theta value over here which is giving us the least amount of value in terms of our cost function, which means that this theta value makes a really good hypothesis which fits the data, most of the data really well. So this graph is really useful and tells a lot to us. Now the only thing that we've got to do is to find this value of theta which gives the least amount of value in terms of our cost function to get a really good hypothesis, right? And the really useful point is that this point on this graph is the returning point of the quadratic equation. That's really good. It enables us to develop algorithms to find that spot for us. Now here is where gradient descent comes in. What gradient descent does is really fascinating and kind of a big brain move. So we start off by choosing a random value for our theta parameter. Let's say we choose this value over here, which we know the value of the cost function for that will be this much. Now what it does is that it gets a partial derivative or derivative for this point in this graph. So what it does is that it draws a tangent to this point. This is supposed to be a tangent, and it calculates the gradient of that line. That's what partial derivative means. And I'm not gonna calculate the gradient for it, but we know for a fact that it has a negative gradient. And then we use this negative gradient value to find a better theta value. So we use that, and let's say we get to a point on here, and it will correspond to this point on the graph. Then that will again have another partial derivative. We find the gradient for that line, and now again we know it's a negative value, but as you can see it's gonna be a little bit smaller value than the previous gradient that we had. Then we use that to get the next theta value, and we keep doing this until we get to this point, and this point is where the partial derivative is going to be equal to 0, and that's when we know we got the perfect theta value for our hypothesis function. Now let's say we start from the left side, and by the way we start this algorithm is by choosing a random theta value. So if we start by this side, we will have a derivative that looks like this, and as you know it has a positive gradient. We use that gradient to get a lower theta value, which will be here. Then we find the derivative again. We keep going to get a lower one until the derivative is equal to 0. So let me write the gradient descent algorithm for you so that it makes a lot more sense. So this is the general form for the gradient descent algorithm. As you can see, this is referring to our cost function. This part is referring to the partial derivative of theta at a certain point, and This is a value which we call it the learning rate. So alpha is basically the learning rate. All right, so let me just choose some random numbers for this graph that we have here to show you what the gradient descent algorithm will do. So let's say we have this point on the graph and it has the value 5 in terms of theta, and it has a value of, I don't know, 10 in terms of the cost function. So we give this to the gradient descent algorithm. Gradient descent will find the derivative for the 0.5 on this quadratic equation. And let's say that the derivative for that is equal to 2. So just remember that what derivative means is that if we draw a tangent line, the gradient of that line, okay, that's what it means. So let's say the derivative is equal to 2. And let's say we have a learning rate of, I don't know, 0.1. Alpha is equal to 0.1. What we do is we multiply this number, this gradient that we've got from the partial derivative, by the learning rate alpha, and we subtract this whole thing from the theta value that we currently have chosen. So in this case, this is going to be equal to 5 minus 2 times 0.1, which is equal to 4.8. Now we go to the point 4.8 on our graph, and then we find the derivative value for that point. Then we will do the same thing for the new theta value that we are on. And the cool thing is that as we get closer to the answer, the partial derivative values are gonna get smaller as well, which means we will take smaller steps to get the answer for our theta parameter. Let's say we start with the theta value in here. We find the partial derivative for it, and as you can see, it's a really steep line, which means the partial derivative value is going to be high. Then we use this gradient descent algorithm to find the next theta value. As you can see, this next theta value is closer to the final theta value that we want to get. Then we do gradient descent for this point. As you can see, the partial derivative is going to get a little bit smaller. So the next step that we're going to take will have a smaller distance compared to the previous one that we had. So if I keep drawing it, will look something like this. You see, each time that we do gradient descent, we take a step to the next theta value, which is closer to the best theta value for our hypothesis, which has the least amount of value in terms of the cost function. You see, it's a really smart way to get the returning point of our quadratic equation. But then you might ask, what happens if we have the quadratic equation like this? Well, trust me, it will never happen in linear regression. But something that you have to consider is the learning rate alpha. If you choose a really small value for it, the steps that you take each time that you run gradient descent are going to be smaller, which means it's going to take longer for you to get the best value of your parameters and thetas. But if you choose a really large one, you might skip the perfect theta value. Let's say we choose number 10 instead of 0.1. Then in that case, this will be times 10, which will equal to minus 15. Now minus 15 in this graph that we've drawn is gonna be somewhere really far away from what we are supposed to get. And if we wanna show it, it will be high up in terms of the cost value that it has. So as you can see, if you choose a really bad learning rate, it might cause some really bad problems for you. So you always try to find the really sweet spot in terms of your learning rate. Now what I suggest for you to do is to choose values like 0.1, 0.0.1, something like this. And in your program, you can print out your cost values and see if they're getting smaller each time that you go through gradient descent. And if they're getting smaller, then it means you've chosen a good learning rate. But if they're getting bigger, it means you have chosen a really big learning rate. But if the cost values are getting smaller but really slowly, it means you have chosen a really small learning rate. So you might want to try to choose a bigger learning rate so that the process gets faster. All right, this is the end of the episode. I hope you learned gradient descent. In the next episode, We might want to learn multiple features for gradient descent and linear regression. And what you've learned so far is like 90% of linear regression. So to recap it, we've learned what the hypothesis is, what the cost function is, and then we learned the gradient descent algorithm that we use with the cost function graph to get the best theta parameter for a hypothesis function so that it fits most of the data that we have. So if you've enjoyed, give this video a thumbs up, ask anything you want in the comment section below, or just say anything you want, and subscribe. Have a nice day.